Yes, with this this presentation, I will show you is about our experience in relation to the design and construction of the Parametric grid shell. This one that you see here in the picture, it is permanent grid shell, and it's built in Lugo in Galicia. And I will show you also all the research that involved from the material to the realization, as the title said. So I will divide this presentation in three parts. First, I will do a short introduction. Then I will wait that I put the pointer. Yeah. Then the sections 2 and 3 will focus on the material and product research that we did. In particular, the work we have done to develop laths of superior properties made of eucalyptus for grid shells, and the comparison with other species and products in terms of minimum radius of curvature, and also in terms of stiffness of the multi-layer system. Then a research that we performed about the stress relaxation is a phenomenon very little studied in timber, but very positive for the structural analysis, as we will see, because you know that the initial stresses due to the carving process are reduced over time, and thereby increasing the structural reserve to resist, to withstand the life loads. And I will end with the work on the design, structural analysis, and the construction and some details of the Parametric grid shell itself. So, of course, I know, we assume that all of you know, we saw already what is an active event or elastic timber grid shell. They are structures that get the final shape by elastic carving of initially straight long laths of a small cross-section. Here you have an example. One of the first timber grid shells built, it is the Frei Otto concept, the German building exhibition pavilion in Essen, and it had 15 meters span. Or this, another impressive work, the multi-hall in Mannheim, one of the most important timber grid shells built to date. It has a maximum span of 60 meters and a very, very small cross-section. It has 50 times 50 square millimeters. So it is really awesome. We could visit it last year, a couple of years ago, and it's really impressive to be down it. And these two are the Well and Downland Living Museum here on the left, and this on the right here, both built in UK with 15 meters and 25 meters of maximum span, respectively. And the maximum thickness they are using in all of these grid shells are really, really small. As I said, maximum 5 centimeters cross-section, so it's interesting. No? So it's apparently a very advantageous technique. It makes possible to build double curved shapes of large span using identical laths and joints with high degree of standardization. But the question is, why is not the construction of timber grid shells more expanded? Why are there so few built until now? So to try to give an answer to this question, I think we must first talk about some important issues that we think are the reason, or at least they are involved in this question, and we will see now. Here I present of the summary of these key issues in the process of the design of a timber grid shell. First, of course, the choice of a suitable wood products and species, which you know that can depend on the product availability on the market. Also, the possibility to obtain good quality long laths if we are going to fabricate our own product. And it is also very important that the product presents high mechanical properties, mainly high bending strength and high modulus of elasticity, because they have important consequences on the design, for instance, on the minimum radius of curvature, as we will see later. The design process, another very important key issue, of course, that it must take into account architectural, structural, constructive constraints, grid geometry, minimum design radius, multi-layer system, as we saw, and all of them are very closely related. Structural analysis, we cannot get rid of it, of course, also quite important. There is a lot of theoretical, or we say numerical research in literature focus on structural behavior of rigid gridshell, of steel, for example, but there is little research on elastic gridshell, and in particular on elastic timber gridshell made of timber. And in this sense, it is important to consider issues such as the joint eccentricities, I mean the distance between the laths that conform the different layers. Also the slip at the joints, important if we are dealing especially with timber gridshells. And the initial stresses due to the carving process and the stress relaxation, as I mentioned before. And all of these are important aspects to take into account, especially to fit the stiffness of the shell and predict the formations or buckling load, for example, correctly. And finally, also the erection process, other case, and sometimes very complicated in elastic timber gridshells. But in many of these topics that I show here, there is in fact really a lack of experience that has somewhat slow down the popularization of this type of structure, we think. For example, there is clearly a lack of treatable products on the market. There is no research on numerical models experimentally tested using full-scale gridshell, or sometimes is necessary a highly specialized engineering for the structural design. So we decided to delve into some of these problems and put them into practice with the design and construction of the pneumatic gridshell. Here you can see another view. And we could say that this gridshell has a couple of unique features. One is the use of eucalyptus wood for the laths, and another one is the structural scheme in the form of a long shell supported only on the short sides. Okay, but I will come back to this gridshell later. I will start first, I think, showing why we decided to use eucalyptus and the research we did to develop high-performing laths with this species. And the first question, of course, was which product to use. We had to meet some requirements for the laths of the pneumatic gridshell, a small cross-section of maximum 50 square millimeters, long length, at least 15 meters, and we wanted also a good quality product. So we started by looking at 3 common commercial products that a priori could meet this requirement, but as we will see it later, it was not so easy work. The first one is the finger jointed solid timber here on the right, on the left. This product is nothing than 2 pieces of solid timber, this and this, glued together by finger joint. And the best known gridshells, such as Mannheim, Dauland, or Saville, use this product. It is the cheapest one and also the easiest to manufacture. What is the problem with this product? The problem is that there are no commercial products made of hardwoods like eucalyptus. Eucalyptus is a hardwood species. There is only commercial product for softwoods like pine, fir, And of course, perhaps we could find a company that could manufacture a custom-made product from hardwood, but we couldn't have the CE marking of such product. And we would also have to perform preliminary testing campaign and a specific production quality control. So this is not so easy process, no? Another very well-known product is the glulam, glue laminated timber, consisting of laminae with thickness between 6 and 45 millimeters per lamina. I'm sure you know it really. But what is the problem here? The problem is with this product is that it's marketed with cross-section too large for gridshells, because it is commonly used for beams to solve medium or large spans. So again, we could probably have a custom-made product with hardwoods, but over 76 millimeters thickness. And we usually need less than this thickness for gridshells, so we have another problem with this. And the third product was LVL, laminated veneer lumber. It's made up of veneers of less than 6 millimeters thickness. This product has a very good performance and is normally supplied as boards, up to 23 more or less meters long, like the plywood is a board. So we could obtain the dimension that we needed for our gridshell. Maybe the only drawback of this product is that it's made from no local species, normally from spruce, and has a lot of adhesive. So therefore, the choice of the product depends on the specific case of the project itself. What about the species? For reference, we have it here. In Mannheim, they use Western hemlock, which is a softwood. In the downland gridshell, they use green oak. This is a hardwood. And in Savile Garden, they use larch, which is another softwood. Western hemlock and larch are softwood, both. But in all cases, they choose quality wood and species from nearby forest resources. So keep in mind that in general, hardwoods are or have better mechanical properties than softwoods. So they are a very interesting choice for gridshells. In our case, we choose Eucalyptus globulus for our PEMADE gridshell. And but why did we use this? You can take a look to this map, even if it is a bit outdated now, but I think it gives a lot of information. Eucalyptus globulus is a temperate climate hardwood that grows as we see in several countries around the world, but in particular in Spain and Portugal, it is cultivated around 50% of the forest worldwide. And in Galicia here, where the PEMADE gridshell is built, there is very much density of these species, as we see here with this color. I'm sure you know the tree. This is the tree. It is very slender, so it's naturally prepared to withstand high bending stresses. Also, eucalyptus, you have to know that is one of the 3 hardwood species in Europe with the best mechanical properties. The other 2 are ash and beech. And it has a D40 strength class, which means that we can calculate with this wood with a characteristic bending strength of 40 megapascals. Keep in mind that common species are about 24, 27, 30, something like that. Pine, chestnut, oak, and so on. And eucalyptus, 40. But in spite of these good mechanical properties and also good natural durability of this species, what do you think is the main use of eucalyptus? Do you know it? Someone of you know what is the main use of this species? No? No answer. The common use of eucalyptus now is for paper industry, for manufacturing paper. So what a pity. So now from the university, we are working there, and we thought it was a good idea to provide an added value to it, and with the development of high performance products, in particular eucalyptus laths for gridshells. How did we do it? How to obtain these high performance laths? I have to say that our research for the PEMA gridshell focused on the first two products that I saw, on finger-jointed solid timber and glue lamp made of eucalyptus. But recently, since last year, we are working also on the development of LVL of eucalyptus. We are getting very nice results also. But let's first to understand the manufacturing process of these two products. It is very easy. First of all, we have the raw material, the sawwood from the tree, but not all the sawwood can be used for structure, keep it in mind. To obtain timber suitable for structural use, it is needed, it is necessary to carry out a standardized grading process, usually visual grading process, by which the size of the defects is limited, and so different qualities of timber are obtained. Once the wood is graded, we have solid timber for structural use. The next step is join the solid wood by the finger joints. And in this way, we obtain finger-jointed solid timber, so we see the first product that we showed before. The strength of this product is determined by the strength of the solid timber or the strength of the finger joints, the smaller of these two strengths. And the problem is that for hardwoods, once more, such as eucalyptus or beech, there are still no standard regulating the manufacturing procedure of this product. So we had to do experimental tests to find out the strength of the solid timber and of the finger joints. And regarding the blue laminated timber, it is in essence made up of lamellas of finger-jointed solid timber glued one top of each other. And there is also no standard for glue lamp made of hardwoods neither. So how do you think we get lots of eucalyptus finger-jointed solid timber of very high performance? Obviously, getting solid timber with the highest possible strength and also finger joint with the highest possible strength. So I'm going to show you first the research that we did here to get high strong solid timber, and then I will show you the research on the high strength finger joint. Okay. So as we said before, Eucalyptus globulus is classified as a D40. That is that we obtain this strength of 40 megapascals if we apply directly the visual grading criteria in the Spanish standard. Directly we obtain the 40 megapascals. But we have tested many eucalyptus boards and we observe a correlation between the modulus of elasticity and the strength. Look at this graph here. The bending strength increase with increasing the modulus of elasticity, which range between 10,000 and 30,000 more or less. So our idea was to make 3 different proposals of qualities, grouping by modulus of elasticity the boards to get higher bending strength than the 40 megapascal derived only by the visual grading criteria. So if we look, for example, at the third proposal here, grouping by modulus of elasticity less than 50,000, from 15,000 to 20,000, and greater than 20,000, we could get very high bending strength, more than 65 megapascal, you see here, in 33% of the boards. So more than one third of the boards. This division into different qualities could be, for example, very interesting in a grid cell with many shear blocks. We could use, for example, the boards of lower quality for the shear blocks, and the boards of higher quality for the grid cell laths, for example. So it's a good option. And now that we know how to get high strength solid timber, the next step, as I said before, I think there is some micro in the. As I said, the next step was how to obtain the highest strength finger joints. And for this, for the highest strength, for the strength of the finger joints, depend mainly on 4 parameters that I show here: the geometry of the finger, the end pressure, is the gluing pressure, I mean, the good quality, and the type of adhesive. So we did also an extensive experimental campaign to study the influence of these 4 parameters using different qualities of the solid timber mentioned before, and 2 adhesive, 1 component polyurethane and melamine urea formaldehyde. So without going into details, I show here the main results. These two columns show the characteristic bending strength of the finger jointed solid timber tested in flat-wise position. You see here, flat, like this one in this picture. Here in the middle is the finger joint. And also we tested in edgewise position, which gives always smaller values. So it is important to know both values. We have to test it in both positions, the boards. And here in this column, you find the short name that we assign according to the results. The number indicates the characteristic bending strength in a conservative way, rounding the value to multiples of 5. So we could get as you see, finger jointed solid timber of eucalyptus with 45, 50, and 55 megapascals. We also tested glulam of eucalyptus of 30 millimeters thickness made of 2 lamina using the timber quality that include all the boards. And with this, we reached 45 megapascals. And we wonder which strength would be obtained if we had tested glulam made from eucalyptus from better quality groups and not just taking all the boards. For example, if we would select the boards with modulus of elasticity higher than 50,000, for example. So we could derive what will happen from this graph here. Here you have, on the vertical axis, we have the bending strength for glulam, for glue-laminated products. And on the horizontal axis, the strength needed for the finger joints. In brown, I show you different strength classes of glulam of soft woods. Here in blue, different glulam of hardwoods, beech, chestnut, oak, okay? And if we pay attention to glulam beech, which is a species very similar to eucalyptus in performance, we see that it shows a linear, almost a linear trend, linear relation between the strength of the glulam product and the strength of the finger joint, you see? So if we took this strength also as reference for eucalyptus, and we take a look to our shallow finger joint strength, these vertical lines here, where the 2 lines cross indicate that we may obtain eucalyptus laminated timber up to GL 48 more or less when we use polyurethane adhesive, or around 60, GL 60 when using melamine urea formaldehyde. And these are really, really very high strength values for eucalyptus glulam. You see, equal or even higher than the best product currently on the market, that is the glulam beech of GL 48 strength class. So what is the conclusion that I want to translate you from this? The conclusion is that in Spain we have a species, Eucalyptus globulus, that is, we can say, on the podium of the species with the best mechanical properties of Europe. And we should take advantage of it, I think. Okay, so having achieved our first objective of getting this high quality eucalyptus laths, I will change topic now to issues related more with the design stage of the gridshell. And in this regard, I think it is important to discuss about the minimum design radius of curvature of different product and species. You are also familiar with this expression, I think, to determine the stresses due to the elastic bending. It's very simple, it's very easy. As you see here, the higher the lath height be, And the higher the stiffness of the material, the higher the stress. And the smaller the radius of curvature, also higher the stress, okay? These stresses, due to the carving process of the gridshell, are reduced over time, as I say, due to the rheological behavior of wood. And this phenomenon is called stress relaxation. Imagine that you bend a piece of wood for a long time, and then you release it. It will not be straight again anymore. It will have a permanent deformation, which means that the stress decreases over time. And this stress relaxation can be written as a function of the time, f function of t. And how we calculate, well, this is the minimum radius of curvature for it doesn't break. And it could be that for which the stresses reach the design bending strength value of the material. So we just change the bending stresses, sigma, by the design value of the bending strength, and we would get the minimum radius of curvature. How do we get this design value of the bending strength? Very easy, just the characteristic value of the material multiplied by K mode, that is a modification factor using wood to consider two features that reduce the strength. One is the master content, and the other one is the direction of the load. And divided by the safety coefficient of the product, gamma m. So the general expression for the minimum design radius of wood will depend on rheological factor, Ft and K mode, factors related to the mechanical properties, the modulus of elasticity, gamma m, and the bending strength, and geometrical factors, B, that is the lath thickness. Okay, so if we forget about the rheological factor, which affect more or less the same, more or less equally different product and species, and we leave out also the lag thickness, and we'll pay attention only to the factors related to the mechanical properties, this E gamma divided by bending strength, we could compare very easily the carving capacity of different species and products. And we can see it in this graph here. We will see. This graph plot the modulus of elasticity and bending strength values for various wood products and species. The slope of the line connecting each point to the origin is exactly this, E gamma divided by Fm. So the points with less tangent can reach a smaller radius of curvature. We can see here that this slope range between 400, more or less 375, 400 and 800, which means that the instantaneous minimum radius varies between 200 and 400 times the thickness of the lath, because it is divided by 2. 200 and 400 times the thickness of the lath, okay? So if we take a look deeper, you see here soft wood of low quality, such as spruce 18, pine 20, here, show the lowest carving capacities, see? In the middle zone, we find glulam hardwoods, such as oak and chestnut, here, and also high quality softwoods, such as larch or pine. And the lowest ratios are presented by the green oak, glulam beech, and also eucalyptus products, you see. So in general, we can say that the higher the timber quality, the higher the carving capacity, as a general rule. As the quality of the wood increase, the strength increase more than the stiffness. and therefore we can obtain a smaller radius of curvature. Pay attention now to this red line here in the middle of the range. It links different species. All the points on this line, on this red line, represent species with the same bending capacity. The species far from the origin will have higher modulus of elasticity and higher bending strength, which means that they will have higher stiffness also and higher structural reserve at equal curvature. So in terms of mechanical properties, the most desirable products for grid shells are those that are far from the origin with the less slope. And this is the case of beech and eucalyptus laminated products of the product that we analyzed. So we have investigated finger-jointed solid timber and glue-laminated timber of Eucalyptus globulus, and I said we are currently studying Eucalyptus laminated veneer lumber. We are getting characteristic bending strength around 100 megapascals. So we would say that would be with Eucalyptus LVL in this zone, more or less, with a smaller radius of curvature. And I think it's a very good options for elastic gridshell. We will share with you the results in the future when we have this work finished totally. And in this picture, we want to represent the minimum instantaneous design radius of curvature for laths of 30 millimeters thickness of different species. Remember the previous slide, the minimum design radius of curvature is between 200 and 400 times the thickness of the lath, we said. So for a thickness of 30 millimeters, it gives radius between 6 meters and 12 meters, depending of the material, depending of the pieces. And with eucalyptus, we find again the smaller radius of curvature that with other species. So we show here also what will reach with LVL of eucalyptus. We could reach minimum radius of curvature in between 3.5, 3.6, and a little bit more than 4 meters, 4.2 more or less. So quite good. No? We could make design that would be impossible with another species. So what is the desirable? The desirable is to minimize the bending strength due to the carving process in order to have as much as possible, as much structural reserve to resist the life load. And for that, a solution, as we said before, would be to reduce the thickness of the lath, but this also implies a reduction in stiffness. And this contradiction is inherent to elastic gridshell always. So this is why we usually go to multi-layer system. We use it most of the time to get more stiffness without reducing the thickness of the laths. So I think we should talk a little bit also about these multi-layer systems. As you know, they are usually solved by mechanically connecting the laths after carving the grid. This way, the composite section provides greater stiffness and the design radius of the individual laths is kept. There are multiple solutions for the connections, as we see here. For example, at the nodes, by means of bolts, it was made like this in the Mannheim multi-hole grid cell. Also, we can do the connection at the members using timber shear blocks fixed with the screws to the lath. It is a detail of the Saville Garden grid cell. Or we could do also at both places, shear blocks at the members and a still patented connection at the nodes, like in Welland Dowland DB Museum grid cell. The decision between one joining system or another is conditioned by the aesthetic criteria that you want, the erection method, the maximum shear force to withstand. There are multiple solutions. Also, the out-of-plane bending stiffness of a timber gridshell is highly dependent on the stiffness and position of the multi-layer connections, as well as other parameters, such as the elastic properties of the materials, as I said before. So to understand how the species influences the stiffness of a multi-layer system, we made a finite element model of a circular arch with dimensions similar to one of the arches in the Parametric gridshell. It has 15 meters span, 1 meter sagittal, and a cross section consisting of 2 layers, two laths of 75 times 30 square millimeters, spaced 60 millimeters apart. And the 2 layers, the 2 laths, are separated by timber shear blocks, joined to its lath by 2 screws of 6 millimeters diameter, in a similar way to the Saville gridshell. And we applied an incremental snow load of, I have it here, 0.15 kilonewton meter on 1/2 of the arch to cause bending until instability. And the graphs below show the load factor versus the maximum nodal displacement for serviceability limit state on the left and ultimate limit state on the right. These blue curves correspond to shear blocks spacing with a spacing of 0.5 meters for the different species, including Eucalyptus, you see here. And this discontinuous black curve corresponds to Eucalyptus for a larger shear block spacing, 1 meter instead of 0.5, okay? So, as we can see, the performance of Eucalyptus is again much higher than the other species analyzed. Broadly speaking, we could say that to reach a given level of deformation, Eucalyptus requires a load increase of about around 30% with respect to oak, 50% with respect to larch, and 85% or 90% with respect to spruce. And also using Eucalyptus with half number of shear blocks, we could also get arches of higher stiffness than with other species with double number of shear blocks. And this is very interesting from an execution and aesthetic point of view, since we could design arches of Eucalyptus with fewer connections, with less connections, and get like this a lightweight appearance, which is obviously nicer, no? Good. So again, I will now let's change again topic or matter and talk a little bit more about the stress relaxation phenomenon that I mentioned before. And for this phenomenon, the first idea that we must have clear in this sense is that wood is not an elastic and linear material. To simplify it, we calculate it at the elastic and linear material, but it is not a linear elastic material. So please look at this graph here. It describes the behavior of a timber beam subjected to constant load. What happened? We see that the deformation will increase over time, you see, until it reaches a stationary value. And this phenomenon is called creep. I'm sure you hear about this. The deformation of a beam is a common problem in timber engineering, so the standards include amplification factors to calculate the long-term deformation from the instantaneous deformation. But remember, in this situation, the load is constant, so we can consider the stresses are also constant over time. What increases is the deformation. However, here we observe the phenomenon of stress relaxation. Now the deformation is constant over time and the stress reduced, okay? So in a timber elastic gridshell, when we bend the laths, there are an initial bending stress due to the carving process that we can call sigma 0, but this stress will decrease over time until reaching a stationary value sigma t. And as I mentioned before, such decrease of initial bending stress, could be very positive for the structural analysis, because it means a recovery of in some way, of the lasts of a certain structural reserve to resist the life loads. So if we represent the ratio between the sigma t and the sigma 0, we will have a function that starts at 1 and decrease with time. If we knew this function, we could obtain the bending stresses of the laths at any time, multiplying it by sigma 0, just like this. The problem is that the stress relaxation is not a common engineering concern. So there is not information on this function in standards, and even there is not information in scientific literature. At least the information is, the little information that we found is not very useful for elastic gridshell, because they are not result from long-term tests using pieces of structural size timber. They are just some results with a small specimen, very short times, so they are not applied. We cannot apply them to this problem of elastic gridshell. So what we did was to perform our own experience, our own experimental test with Eucalyptus laths to obtain this function ft. And for this, we designed a specific device to perform this test, this machine that you can see here. The approach is very simple. It's just bend the laths with a constant radius by applying a moment at each end using 2 levers that incorporated load cells. And the load cells were recording in time the reduction in stress. This is an elevation of the machine with the geometrical control parameters to get this constant radius. And we could test 6 laths at the same time. So we could study different radius of curvature. In particular, we tested three different radius of curvature that produced initial bending stresses of 25, 50, and 75 megapascals. Here you have the corresponding radius of curvature, 360D, 180D, and 120 times the thickness. And in this graph are the result of 2 years measuring, although the machine is still measuring. And I think 7 years, Antonio, more than 7 years. But now there is not so much difference as what we measure with 2. From an engineering point of view, we could take the most conservative values that correspond to 0.75 for 1 week of reduction, 0.66 for 6 months, and 0.50 for 5 years, which is equivalent to the long term, okay? 0.50, this ft function that we were looking for. Okay, so finally, after this research on the material that I show you very briefly, I will show you some details of the Parametric gridshell. The project was completed about 6 years ago in the framework of an European research project called Lugo Must Be plus biodynamical. It is a multi-scale research project which develops several actions from forestry action to urban scenarios. And the task in which we particularly well involved had the objective to develop products and construction systems using local species, local materials, in particular these grid cells made of eucalyptus wood that I saw. And I will play now a short video of a couple of minutes that we prepared as a presentation of the project. I hope you can hear it well.
Más Biodinámico is a research project that focuses on improving Lugo's ability to adapt to climate change through forestry actions and sustainable construction using wood. In this project, the Platform for Structural Timber Engineering, PMADE, of the University of Santiago de Compostela, is developing new structural products made of Galician species in order to encourage the replacement of other materials with high energy costs, such as steel and concrete. One of these products is the gridshell. It is built using straight timber lathes of good quality, great length, and small cross-section, which are curved and crossed in successive layers in the same way as fabric. It is an innovative and structurally efficient solution that achieves strength by its curved shape, requiring less material than other conventional solutions. It is of great interest for lightweight roofs with medium and long spans, suitable for both free and modular geometries. After several research and technological developments conducted in collaboration with local companies of the sector, an experimental prototype of 24 meters long has been carried out to cover the new PMADE wood storage in Lugo. The objective is to implement the structural system and perform the monitoring in medium and long term for application in future actions.
Okay. Antonio is telling me that that the video he couldn't see the video with much continuity, so you have here the link. We are recording the presentation, so if you are interested, you can watch it. Okay.
Can you paste it in the chat?
Sorry?
Can you paste the link in the chat?
Ah, okay.
Well, no, it's.
I think it's. I have.
Okay. Don't worry. I'll look for it.
I can do it later. Yeah, when I finish, I look for it. So let's go now to the design and structural concept. It was designed to cover a new wood store facility at the Timber Engineering Laboratory of the University of Santiago de Compostela in Lugo, in Galicia. It is 24 meters long and 15 meters span to allow the storage of long timber elements before and after testing them in the laboratory that was behind here. It has 7.5 meters of highest elevation and 4.5 of free front, considering big lorries that pass through here. As Enrique said, it is the first permanent elastic timber gridshell built in Spain and the first in the world made with eucalyptus. But as I mentioned at the beginning, maybe the major interest of this elastic gridshell, apart from the species, is the structural concept. It has a long shape supported only on the short side on two glue lamp arches of 3 meters radius, which offer new and interesting architectural applications, I think. This was a novelty and a challenge, since previous elastic timber grid cells built up to date were supported around the whole perimeter. In this case, it works longitudinally, similar to a large beam, making cantilevers very interesting to reduce moment at midspan and rotation in the supports, as well as protecting the stored timber material from the rain. So the grid layout consisted of 3-direction open laths to provide out-of-plate bending stiffness. These two of these are arranged longitudinally and generate a diamond pattern that lay on the supports. And the third one, in the transverse direction, triangulates the grid and also work as a bracing system. But due to the small radius of curvature in this transversal direction, the laths must have very small thickness. So it was used a mechanical lamination of 3 thin pieces to achieve the needed thickness. The glulam arches rest on cylindrical supports embedded in the foundation, and there are also kind of movable joints of steel also arranged at the upper part of the support to allow an easy fitting of the 2 arches during the construction of the gridshell. Then it was covered externally with a translucent white textile tensile membrane of PVC, which allowed the transmission of natural light and avoid the direct ultraviolet rays inside. I will talk also a little about the design process. There was an iterative process between the design and structural analysis stages to obtain the final shape and meshing, for which we developed an integrated design tool in Grasshopper composed by 5 tools: a grid tool, a Gridbill tool to mesh the surface, a bending evaluation tool to obtain the initial bending stresses due to the carving process, an optimization tool to obtain a grid with the minimum initial bending stresses, a graphic output that provided a 3D model with the actual thicknesses for the development of the engineering details that we needed, and finally a data output tool that provided a list of data for carrying out the numerical model. I will go a little bit deeper in these two, in the Gridbill tool and bending evaluation tool. The Gridbill tool performed the surface meshing following a geometrical approach by applying the compass method that I think all of you know. You can see the concept here on the left. We have 2 curves. The 2 curves are first drawn on a free surface. Then the curves are divided into equal segments by spheres of equal radius. Then, using the intersection point as centers, the complete surface can be meshed. It's easy. No? So here on the right, you see this concept applied to the Parametric grid shell. And we use 2 geodesic curves as master curves, this one here. Here you find the extended surface in order to fully mesh until the edge, and the trim surface, and the final families of laths. Even if the analysis resulted in good stiffness for vertical loads, the stiffness at the central area of the longitudinal edges was not enough against horizontal loads, like for example wind. But instead of using steel beams or timber beams or big cross section that were common solution in such cases at the boundary, we decided to project that third family of laths in the transversal direction, which work as bracing system, and the Gridbill tool could also generate this third family of laths. The algorithm also generate the multi-layer grid by introducing the thickness of the laths. We can see here the detail. And the algorithm also show in real time the carving stresses of each family of laths. The stresses were obtained through normal and geodesic curvature with the expressions that you know. And here I saw an example of the carving stresses due to the normal curvature. Okay, so after this brief approach to the design, I will talk about the numerical model. As we said at the beginning, one of the key issues of the numerical model of a grid cell is to correctly adjust the stiffness. The stiffness has very much influence in the stress, in the deformation, in the backing analysis, and everything. So in order to calibrate the stiffness of the numerical model for the PMADE grid cell, we performed previously a full-scale test on a smaller laboratory prototype, but that worked very similar. Here you see the prototype of the laboratory. It was a 7 meters span and also rested on the source side in a similar way than the PMADE, but in this case on two semicircular LVL support instead of on two arches. Okay. We loaded the prototype with water containers, you see them here, and we measure by photogrammetry the displacement of the intersection points and also at the middle points of the laths. In total, I think it was around 150 target points, more or less. Here is an interior view with the 50 liters water containers hanging from the grid cell. And here, the three types of joints that we use. All of them solved by mechanical fasteners that produce a slip at the shear planes. This is the grid nodal joint, the type 1 we call. It consists of 5 eucalyptus layers, 2 of 6 times 25 square millimeters, and 3 here of 60 times 8.3 square millimeters that form this lath that I said before in the transversal direction. And all of them connected by a screw of 6 millimeters diameter. This joint here in the middle is the joint of the grid cell to the semicircular LVL support, the type 2. And we use for this screws of 8 millimeters diameter. And this one is the mechanical lamination of the 3 pieces of the transversal lath that we saw here from the side. Okay, here we see it from the front, and it was joined by 4 millimeters diameter screw within a space of 60 millimeters, one from each other. And I will very briefly present here the strategy for the development of the finite element method, finite element model, I mean, for the structural analysis of the laboratory prototype with a focus on the stiffness calibration. We use for this Drupal software. I don't know if you hear about this, Drupal. And the model consisted of including the actual eccentricity of the joints, the real eccentricity, and the existing interlayer slips. Okay. And for that, we implemented a system of couplings aligned in the actual position of each connection. One end of the coupling was located on the longitudinal axis of the lath, like this one here, you see, and the other end of the shear, the other on the shear plane. Okay. At that shear planes, the couplings incorporated 2 springs perpendicular to each other that allow only movements perpendicular to the axis of the connector. And in the case of the grid nodal joints, it was also a low rotation around the coupling axis. The stiffness of both springs was assumed to be identical using the Eurocode values. And this is concretely the case, this one that I show here, the case of a grid nodal joint, the joint type 1 with 8 aligned couplings. Here you can see the final model of the complete structure. Above, the 3D model in Rhino with the points obtained from photogrammetry and a detail of the nodal joint. And here down, the 3D model made in Drupal. We analyze also the influence of the LVL supports, this one, and the stiffness of the joints on the overall stiffness of the grid shell to better understand the behavior of the structure. So we develop several numerical models with and without LVL support and with and without a slip at the joints for the 3 types of joint that I showed you before, okay? And here I show you some results of the models. Models 1, H1 and C1 have all the joints rigid, I mean without a slip. Model 5, H5 and C5 have a slip in all the joints, okay? Without a slip and a slip in all the joints. And the rest of the model, 2, 3, and 4, have a slip only in some of the type of the joints, okay? And to summarize, I will only discuss models 1 and 5 and the main experimental results that I include here in the first column. So this first row shows the sum of the displacement in absolute value for all the nodes. It provides an overview of the deformability of the structure. The second row represents the ratio of the above parameter for each numerical model in relation to the experimental one. And the following rows here show the displacement corresponding to some control points, particular control points. So as can be seen, the S models without LVL supports underestimate very much the displacement of the nodes and show the great importance of including the structural support elements in our models, in this case, the LVL support, okay? And comparing, for example, model C1 and C5, both with LVL support, it can be seen that model 1 with the non-slip joints underestimate significantly the deformability of the structure if we compare it with the experimental one, you see. Only the model 5, the C5, which include the semi-rigidity of all the joints and the LVL supports, achieves a reasonable fit between the experimental and the numerical results. So it's important to make these full models in our studies. This figure shows the final global deformation of the C5 model and the deformation of the 3 transverse arches, this one, and this one, okay? And as you can see, the fit of the model in blue with the experimental results in gray is good, okay? However, we can make 2 observations. The deformation at the loads application points is higher in the experimental test, if we take a look here, see, than in the numerical model. Also, the maximum experimental displacement in this area here, was around 14 millimeters more or less, which is below the maximum value of serviceability limit state, that is around 20, okay? The stress in the joints may exceed the service range due to the application of heavy concentrated loads. And this could lead to local effects not considered in the model, for example, non-linearity phenomena in the slip of the joints. And another observation here is that the greatest displacement of the structure does not occur in the load application point. It occurs in the lower part of the transverse arch here, which glows inwards when the vertical loads are applied. And this behavior highlights the lack of stiffness of the structure in this area and points to the need for design modifications to increase the gridshell stiffness in that zone. For example, using what I said before, H-beams, large cross-section, or increasing the moment of inertia of the transverse laths. That is what we did. The solution was applied in the PEMADE gridshell using double transverse arches here. And finally, for the analysis of the PEMADE gridshell, it was used a numerical model similar to the one presented for the prototype of the laboratory, but in this case using the software robot. It followed the next step. First, we created the geometry from the list of data provided by the parametric tools, including the local axis, rotation, and joint eccentricities. We implemented the initial bending moments of all members, also obtained from the parametric tools as pre-stresses forces. The bending stress relaxation that we determined experimentally with the new machine was included as a bending stress reduction factor of the initial pre-stresses forces. We consider linear material and nonlinear geometric analysis with the geometric imperfections. We also consider the slips of the nodal joints obtained from the shear test. And we perform serviceability and ultimate limit states analysis according to Eurocode 5. Okay, so having the design, I will finish with some engineering details and the construction process. This is a picture of the manufacturing of the Eucalyptus laths. The machine that makes the finger joints to get the finger jointed solid timber, our product, has a limitation in length of 9 meters, and we needed 25 meters long for the PEMADE gridshell. This is always a common problem. We will always have a limitation in the maximum length of the laths. Limitation because of the finger joint machine, or limitation because of the transport. So it may be necessary to make connections on site between the laths to get it longer product. Here you see two typical solutions for these connections between laths. Here on the left, a mechanical joint that was made Mannheim gridshell. It's not so nice, I think. And here on the right, a scarf joint, you know it. It was done like this in Savile and Downland gridshells. And also we choose this one for our PEMADE gridshell because we thought that aesthetically it was more invisible joint. This was quite a tricky work because these joints are inclined. It has an angle. In addition, glue joints need controlled environment conditions. So we had to make them indoors and build 25 meters tables to place them on. You see here, and it was really an unforgettable work. We also test them. We determine the bending strength of the scarf joint using different adhesive, but I will not bore you anymore with numbers. I will just tell you that the adhesive that provided the best result was polyurethane formaldehyde. So was the one that we used. And we continued the experience with the arches, the laminated arches. And we always say that one of the biggest learnings in this project of the PEMADE gridshell was that in Spain there are no manufacturers that make glulam timber arches of less than 4 meters radius due to restrictions of the machinery of the machine, of the pressure machine. And we projected our grid cell with 3 meters radius, glulam arches. So we have to laminate our own arches by hand, as it is done in traditional way. Here you see, we made a formwork, and very, very carefully we were gluing each lath and giving pressure to get the final arch. So it is important to be clear about the manufacturing limitation of the machinery for our designs before. Okay. The upper here, the upper edge of the arch is a warped surface, and here, and the ends are carved, so the shape had to be made by CNC finally to get these round shapes. Here are some pictures of the manufacturing process of the steel supports and the movable joint fabricated with the same curvature as the timber arch for perfect fitting. These movable joints can move along this tube and also rotate, so it makes the assembly of the grid cell easy, and also adapt to possible manufacturing errors. This is the nodal joint. The 6 layers of laths are joined by a M12 bolt, a 12 diameter bolt. These 4 laths in longitudinal direction, represented in gray here, are made of glue laminated eucalyptus with 75 × 30 square millimeters cross section each one. And these other 2 laths in the transversal direction, represented in blue, are the ones acting as bracing system that I mentioned before. And they are sold with 3 laminae of 10 millimeters thickness each one, mechanically joined by the screws. So in PEMADE grid cell, the shear blocking between the laths is solved in each joint, in a very simple way, without the need to use additional shear blocks, like in another grid cells. And I think it gives a likeness appearance, I think. This is a detail of the anchorage of the textile. It is solved by a steel round bar joined by steel plates to the grid cell. So the membrane is tensioned against the structure. The stresses of the tensile are transmitted to the 2 layers of the grid cell through timber blocks placed at the ends of the laths, this one that you can see here. And we place it a thin timber lath, thin spacer, we said, on the bracing laths to avoid damage to the textile during installation with the head of the bolt. So we did this. Here you have some pictures of the construction process. We decided to place the laths individually on a formwork according to the grid position that gave us the lowest bending stresses. We knew this position from the meshing and optimization stages, so there was no problem in doing like this. And this is the first group of laths, and this is the grid cell almost finished. And the lifting process, it was carried out using 2 cranes that raised the grid cell by the 2 arches, here and here, and position it on the support, on the mobile joint that were waiting here. When the lifting process was completed, of course, the movable joints were welded, so they cannot move anymore. And here you have a view of the grid cell after covering with the textile. Here you can see again the structure, but completely finished, closed by a translucent perimeter wall. This is the appearance of the grid cell from inside, from down. The eucalyptus laths were finished with a luxure of dark color to emphasize the contrast of the grid with the pine arches and also with the white textile. This is a closer detail of the bolted nodal connection. This picture, you can see the curvature of the laths, I think, very well. This is an interior view during the first storage. It was a moment for remember. And a detail of the movable steel joint here. Here you see what I said before, the curved shape of the arch end that we did with the CNC machine. This is one of the cantilevers of 5 meters long in one side. This is an eye view from the cantilever side. And this is another one with the light on. We wanted to get this effect of a grid lamp when we switch on the light, so I think it's nice at night. And okay, that's all. I hope you like it, and if you want to know the activities that we are doing on timber and gridshell at the School of Architecture in Madrid, we usually post it in our Instagram profile at Almudena, in case that you are interested. And that's all. Thank you for your attention.